Hello again. Alright, so let's continue with two more plots, or rather two more parameters that we can derive from your time plot, from your compression curve of the odometer test. So you say if you look at this plot, it's the same as the previous one, but now instead of just loading one line A, B, C, it has got this unload point. So you load say 24.5, 25, 50, blah 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 until 800, and you go back 400, 200, 100, then you go back again 200, 400, 800. Can you see? First observation, you see that when it is being reloaded, it will come off to point F, a settlement that is greater than before, right? What is that supposed to mean? It shows that the soil is trying to sustain the bigger load, and because it is already equivalent to what it has previously sustained. Remember the pre-console pressure, so there's a new pre-console pressure there, so you just go down a little bit more, right? The slight one. And the thing with this plot is that once we have got the unload and reload loop, as you see here, unload, reload loop, we could draw a line through the loop. And what is the purpose of this line? This is an unloading reloading line. The purpose of it is that you can then use it, bring it up through your plot, right, as a parallel line, to find where was your initial pre-consolidation line. Because you see, when you take a soil from a certain depth on site and put it in the odometer and run the test, because of all the disturbances, we usually cannot find. We cannot determine where is the original pre-console line. And if we can't have this line, the correct line, then we cannot have the correct E0. E0 is the initial void ratio, so the initial void contents in there, right? As filled with water, obviously it's fully saturated. So this is how we usually do conduct the odometer test, do an unload reload loop to identify the pre-console line. If you keep doing this, right, load unload, go down more, load unload, you find that the lines that you draw is always parallel. Alright, it's because every soil has a certain signature, its identity, so it's the same. Okay, and the last bit of information that you can derive from the compression curve is what we call the compression index and also the recompression index, right? CC, CR or C alpha, depending on which book you're looking at. So again, your load is an original compression line and this is an unload line. So by right, this should be unload and reload, and you draw a line through it. That is and that gradient is your recompression index, whereas along this vertical part of your compression curve, there's your normally consolidated line. We talked about that before. This gradient is your compression index. This is the value that we need to use to calculate your settlement. We'll see one example later on, don't worry. Okay, so these are the two gradients that you need to find. And remember, there are two lines to see. This recompression line is a parallel one to the initial one, so you can draw this and then bring it up to make the correction for the first one that you may not have. Okay, now let's go into more detail about this settlement, the immediate settlement, consolidation settlement, and also creep. So you recall we talked about this earlier on, about immediate settlement. That is this part of the curve. When you first load it up, it's going to have a certain deformation. Remember, it's a deformation that is temporary because it's elastic, right? Because of the soil slightly rearranging itself. When you take out the load, you still bounce back. And a lot of times it's just air cushion, alright? And air is, if it's still entrapped in there, you pop the load, it will just compress a little bit. So it will expand a little bit sideways, and as you can see in this diagram here, expand a little bit sideways and go down a bit more. A bit vertically, but when you take off the load, it will come back. So if you look at the equation to calculate or estimate your immediate settlement, you can see this parameter in there, mu. Mu is your Poisson's ratio. Whenever we see mu in the equation, we know that the material is considered to be fully elastic. So that is what it is. And in order to use the equation, E is your Young's modulus. You could look at the influence factor in table 2.8 in your module for I. Alright, it's straightforward. Next, we look at the consolidation settlement, which is the main bit, alright, the primary part of any settlement, because this is the largest settlement that you get from a load being popped onto a structure, and this is the one that is taking the longest time. So this is the part, as you can see in the curve, it is taking the longest time and contributing to the most of your settlement, alright. So for a settlement, for consolidation settlement, we just go back a little bit. You see that this part is where the water is being forced out of your soil. And as we load, you see that soil is going down, water is going out. So the load initially that is being applied is being taken up by who? By the water first, because water is more compressible. So when you put the load, the water will take the pressure, and the water doesn't like the pressure, alright? So initially it's excess pore pressure 0. There's no excess. The pore pressure is as it is. When you put the load, say 100 kPa, suddenly the water pressure increased by 100 kPa. It doesn't like it. What will it do? It will start to escape from the soil. And that is dissipation of the pore water, excess pore water. And when the water starts to go out, what will happen to the soil? Overall, you see it going down. That's settlement. That's why it goes back to the original assumption why we must assume the soil to be fully saturated. If it's not fully saturated, when you put the load, the settlement that you observe may not be totally be attributed to the water going out, right? And when the water goes out, the voids that are being left behind, they fill up by the soil particles. Can you see? The preview videos I sent you, if you look at that, you have understood this, right? The soil become more nicely packed, more densely packed, hence they become stiffer. So next time you put the load on it, it will not go down that quickly, that easily anymore. So that's the whole point of it, right? Just very quickly, this is last bit of your curve. There's a secondary compression, or we call creep. As the name will tell you, creep. It takes a long time. Soil will always settle. Alright, if it is not being applied a load that is larger than what it has previously experienced, that means it wouldn't undergo consolidation settlement. It will still go through creep, meaning that the soil particles, for instance, soil grains are a bit like, if you like, rice grains, like baras. So they may be setting like this. So with time, slowly, this fella is not comfortable. It will slowly want to lie down. Can you see? And this slow movement of slowing, lying down, going flat, going into stable, more comfortable position will cause a secondary compression. And that's creep. It takes forever. So if you like, this line is actually asymptotic, meaning that it goes into infinity. Right. Out of this time plot, we could derive the coefficient of consolidation, that is CV. Okay, and there are two methods here. One, as you can see here, plotted out in a log scale. As you can see, the time is in log scale. We use the Casagrande method, right? And the time factor used is T50. You can look it up in your module or on the internet. There's a chart to it. If you don't know, you can calculate. There's a formula to it as well. It's 0.196. And H is the drainage height, and T50 is the time for 50% of your consolidation to take place. So this is a graph. How to determine T50 if you want to use the formula? First, just extend the straight line bit of your plot down, and extend backwards your creep bit, right? Can you see? And you get the first point. Next, that is your U100, right? Next, you are going to try to find your U0. That is initial void ratio, or the initial void ratio, or the pore pressure when it's 0, right? When nothing was happening. So what you do is that you just find the most curved bit of your plot and put the point there, right? And measure the distance from your y-axis to that point. That's the time, right? So it's t. So all you need to do, say this t is 1 minute, so go to 4 minutes, that's time 4, bring it down and see the third point. So the distance, just measure it, the distance of x, that is the distance that you want to bring it up, and find your U0 line. Simple as that. It's very graphical. Okay? And that's where, if you know U0, and then you know, if you know U0, you know U100, of course you can find U50, it's right in the middle. Okay? So that's how it works. Once you get a number, you pop it in, you can get your CV. The second, before we go to Taylor's method, second method, let's go through a quick example of how to calculate CV. Alright? So, first case, first scenario. The first thing first, this is a clay that's compressible, sandwiched between two layers of sand. Okay, sandwiched between. That is important to know, is sandwiched between, it's not underlain by rocks or things like that. Second thing to take note is that your T50, as I said, if you don't like to memorize this, you can always remember this formula and start calculating, you get 0.196, right? And because the soil, the clay, is being sandwiched by two layers of sand, top and bottom, it is a doubly drained soil layer. Meaning what? Meaning that the water that is coming out from the clay is going up and down, so you got to take the center line. And when we calculate settlement for any clay layer, we are taking the center line or the mid height of the clay layer anyway. Right? Got it? Double drain means you got to divide the sample height or the clay height or the clay thickness into 2. As you can see here, the drainage height is not the full height of 0.9902, it's 0.9902 divided by 2. Then once you get that, put it into the equation and you get the number there. Simple as that. So where can we go wrong? We can go wrong. Number one, we refuse to memorize this. T50 is 0.196. Number two, we get it wrong. It's double drain or single drain. If it's single drain, meaning, for example, the bottom here is not sand, it's rock. So water cannot go down. So the water can only go upwards. So the drainage height is going to be the full drainage height. There's no divided by 2. Right. The second method that we talk about is the Taylor's method. Now, the time is plotted in terms of square root of time. It is no longer on the scale of a log. So when you do that, you find that your curve will become a straight line followed by a sharp curve like this. Right? That's a red line. And in order to determine your T90, right, to use Taylor's method, we are looking at T90. We are not doing T50 anymore. 90%. The time for 90% of consolidation to have taken place. Point 1. Just take extend the straight line portion of your graph, right, and bring it down. Take your ruler, right? Literally take your ruler and measure out the distance. Say this is 1 cm, alright? And measure out where is 1.15 cm. It needs a 0.15 extra, right? That's the point. Draw a line from this point to the origin, okay? When you do that, you see that you intersect your curve at point C. That is your U90. If you know where is U90, of course you know where is the square root time of your T90. Remember, this is square root time. So when you use it, put it into the formula, you must have it squared as well. So what's the do? So that the square root is taken away. Don't simply just take the square root of this number and put it in. You got to square it again. Got it? And notice here that T90, the TV for T90 is actually 0.848. Again, you don't like it, you can use that formula that I showed you earlier. Okay. And very quickly, this is being explained more in detail in your module, but I'll just take you through it briefly here. When we load again the foundation, you load it, and we notice the pressure bar, it goes down to 2B. That is all that it matters, because anything more than that is already very negligible. I mean, in terms of stress increase. And this is your clay layer. And we say we are interested only in the mid height, but we need to know throughout, right? So the stress is being distributed as it goes deeper, it gets less. And you are going to divide up your soil into 6 layers here, and you can see where the transition is happening. Curve a bit more. This is almost the same here. This is the part that's transition. You will divide them more. You see? In part 4, you have part A and part B here. So you just want to capture the transition, the changes. So the place where it is more sensitive to it, to the change in stress, you just put in more layers and calculate more layer by layer. Alright? This is an example. Forget about the units there. All we want to know is how you can calculate settlement by using the parameters that you derive from your odometer test. Very quickly, this is a situation. You have your clay layer, and now and the bottom is impervious, meaning that this is single drainage, right? So now you want to put in a backfill, and the backfill is 20 feet high, and it's given that your gamma is 100. This is in pounds square feet, yeah? So don't bother about the units. First thing first, the original load at mid-height, remember, we want to calculate settlement, is always on the mid-height. At 25 feet is simply taking your gamma. Where is your gamma? 100. Yeah, it's 100 here. Multiplied by 25. But because there's groundwater table here, remember, you got to minus it off. So this is 9.81 actually, but in pounds is 62. Multiplied by 25. So this is your existing load at this point A. But don't forget, you put in the backfill, this is additional. So the additional is what? 100 times 20. So plus your 940, so it's 2940 here. So put into this equation, you can see here, what is the settlement that's going to happen under this load? It's going to be CCH 1 plus E naught. Everything is given. CC is also given. Just put it in. Where can we make a mistake? Here. This is log of something over something. So if you don't like it, it's log 2940 minus log 940. This is what we learned in MS. Yeah? Do not forget that. And you get the answer. So in this case, the settlement will be 4.5 foot, 4.5 feet here. Okay, we pause here for a moment.